Hello everyone. This clip consists of 6 sessions, focused on the technique of completing the square and the application of it, especially the graph sketching in calculus. If you are asked to sketch the graph gx equal to 2x squared plus 5x plus 7, what would you do? I bet many of you would take the derivative of the function. But have you ever recalled how you sketched it 2 weeks ago before you have learned such technique? The objective of the clip are to apply the technique of completing the square for quadratic expressions ax squared plus bx plus c in different cases, and to sketch the graph g of x equal to ax squared plus bx plus c with transformation of graph f of x equals to x squared like this. In the coming sessions, we're going to investigate quadratic expressions ax squared plus bx in the view of completing the square. We will start with the case where b is an even number. In this session, I try to explain why we have the technique named as completing the square. But let's pick a number for b first. You may choose b from 2, 4, 6, 8, or 10. In each case, you could see the value of b changing. You may click on Random button to let the worksheet choose for you. This time, let us choose b as 6. Click Done. Why do we call such technique as completing the square? You may click the box for the answer. As you can see, if we consider the original expressions as the area of something, then x squared could be the area of the purple square on the bottom left, with the dimension x times x. Now, consider each of the red rectangles. Each of them has the dimension of x times 1, right? And so, 6x of the expression means the sum of the area of the rectangles here. And the original expression, x squared plus 6x, could mean the area of the figure, the whole figure, in front of you. Question comes. You are asked to enter number of tiles to be added to complete the square. What does the square refer to? Look at the top right-hand corner of the figure. With careful observation, you could see if we could fill the area here, a little big square would be completed. And the empty missing area is also a square. Look close, you could see its dimension as 3 times 3 in this case. Can you tell the number of tiles we should add? In order to fill the big square, how many square tiles are needed? Of course, here each tile will have the dimension of 1 times 1. Do you get the answer? I guess we need 9 tiles. Let's see what happens if we add those 9 tiles in. Look at the graph here carefully. Now, can you see a large square up here? I'm sure you got it. When we add the 9 squares to the original figure, we actually make the whole figure into a big square. That's why we call such method completing the square. Here comes the last question of this session. What is the length of the completed square? Let's see. We have x 1, 1, 1 here. And we have also x 1, 1, 1. So that is x plus 3, isn't it? Now, it is your turn to build up this concept in your mind. Open the worksheet, square seal 1, and try yourself. This is the end of the session. Pause the clip and come back the next session if you are sure you get it. Welcome to this session. In this session, we want to extend the value of b to some other odd numbers. Just like last time, you could pick the value of b. And this time, you could pick any positive numbers from 2 to 10. Let's try 5 for now. I'm sure you still remember how we treat the original expression. The x squared here acts as the area of the small square on the bottom left. But how about 5x? In the previous example, 6x could be separated into 2 groups. One group is put on the top left, while the other is put on bottom right. Could I put 3 on top left and 2 on bottom right here? Could I put 3 on the top left and 2 on bottom right? I don't think so. Why? As you know, we want to complete the square, that is, the big square. So, what could we do? Let's see the graphical view before we could draw any conclusion. Oh yeah, we could actually divide 5x into two groups of 2.5, right? Then we could still be able to complete the square, but not a rectangle. The problem comes again. How many tiles do we need to complete the square? Don't worry. Instead of counting the number of tiles on the top right, we could actually know the dimension of the top right square as 2.5 times 2.5. At this time, we could do some easy multiplication. 2.5 times 2.5 is 6.25. So we need to add 6.25 tiles to complete the square. Just like last time, we could see what's going on after adding the tiles. You could see 4 complete tiles to be added as indicated. 4 half tiles should also be added, 2 on top and 2 on right. 1 quarter tiles on the very top right should be added here. Now, I'm sure you know the length of the completed square. X plus 2.5? Exactly. Now, it's your turn to build up this concept in your mind. Open the worksheet, square O2 and try yourself. This is the end of the session. Pause the clip and come back the next session if you are sure you get it. Welcome back. In this session, we want to see how we could handle the cases where A is not equal to 1. In particular, A equals to 2. Suppose that we have the expression 2x squared plus 10x. By the previous knowledge, we understand we need to complete the big square. Since we now have 2 instead of 1 squares with dimension x times x, we couldn't put them together at the bottom left, just like the reason why we could not divide 5x into pair of 2x with 3x in the previous example. So, what could we do? Let's see if there is any hint from the graphical view. If we try to complete not only one big square, but some big squares with same area, then we could simply divide 2x squared into two groups, each with area x squared. And so we could further divide the 10x into 4 groups. I repeat, 4 instead of 2. 1, 2, 3, and 4. And you could see actually we need to add some tiles to complete the 2 squares with same area in this case. You may wonder why we are completing 2 squares instead of 1. But let's pretend to do so first. The reason could be found in section 6. Now, we want to settle the same problem as before, the number of tiles needed. With the graph in front of you, or you could now have the images in your mind. You know we need a total of 12.5 tiles as the length of the top right square is 2.5. Thus, 2 squares will count for a total of 12.5 units. As usual, we could see the effect of adding tiles and the length of each completed square, as mentioned. X plus 2.5. It is again your turn to build up this concept in your mind. Open the worksheet, square 03, and try yourself. This is the end of the session. Please start the next session if you are sure you get everything. In the previous sessions, we discussed the original expression of ax squared plus bx. What if we change the addition sign to subtraction? Let's say we have the expression x squared minus 4x. We know that when we have x squared plus 2x, we are adding 2 pieces of rectangles to the original square. Then x squared minus 4x should be treated as subtracting 4 rectangles from the square. Yes, you're correct. Let's see what is happening. You could see the purple square here, just like the square having dimension x times x. If we try to take away 4 rectangles, each with dimension x times 1, we could actually take 2 from the top and 2 from the right, like this. We may have 2 investigations here. First, the small area here on the top right, as you can see. 4 squares, actually, are being cut 2 times, and you know it is not possible to cut out some parts from the original area twice in the physical world. Second, we could see that the remaining part is still a square, and it is the square to be computed in this situation. Therefore, if we add back the 4 little squares, we are computing the little square here. By the way, how many tiles do we have to add to compute the square here? You certainly know the answer is 4. The 4 tiles we add here is to replace the overcutting pieces. That is, the orange region you could see here. What is the length of the computed square? Great! The answer is x minus 2. This is the end of the session. Please take some trials and come back afterwards. In this session, we will discuss transformations. Given a function f of x as indicated in orange, do you still remember what the functions f of x plus c and f of x or plus d look like? Let's make c equals to d, say 3. Now I first click the option f of x plus c. When c equals to 0, then f of x plus c is just the same as f of x. So, 2 curves overlap the others. I will now change the value of c from 0 to 3. I'm sure you could see the graph moves to the left-hand side for 3 units. If you are not sure, check the point I am showing you. Every point on the new graph is just 3 units on the left of the original point. Next, I will show you the graph of f of x or plus d. Except when d is equal to 0, then the graph would just overlap with the original graph. Now, I will change the value of d from 0 to 3. This time, you should see the graph moves upwards and with 3 units. I could show you the reference point for justification. Alright, if I make c equals to 2, and d equals to 1, we could see the individual graphs, which is 2 units to the left and 1 unit to the top, respectively, from the original graph. Can you guess what function of x plus 1 or plus 2 looks like? Yes, the original graph is transformed like in 2 steps. First, moving upward by 2 units. Then moving left by 1 unit. The new graph would be like this. The dynamism effect is not the main dish of this clip, so I would rather leave it to you. You may take a look and feel free to try. Come back for the last session when you finish. Hello everyone, this is the last session of the clip. In the previous sessions, we discussed the geometric representations of completing the square. We had also discussed the transformation of the composite functions. It is time to conclude all the methods here. As usual, you may change the value of a, b, and c of a function, but I will use those we had for demonstration. Let's start with g of x equal to x squared plus 6x. Our objective is to present g of x in terms of f of x, where f of x is equal to x squared. Now, we have g of x equal to x squared plus 6x. Think about when we try to complete the square, how many tails we have to add, and what would the length of the outcome square be? Hope you still remember. We need to add 9 tails with the final length x plus 3. Using simple algebra, we could simplify the function into x plus 3 all to the power 2 minus 9. So, we could also rewrite it as f of x plus 3 or minus 9. Take a look on this. F of x plus 3 or minus 9. Can you sketch it when you are given the graph of f of x? With what we have discussed in session 5, you know we could obtain it by shifting the whole graph to the left by 3 units, then to the bottom by 9 units. What is g of x is equal to 2x squared plus 10x? I hope the geometric representation will still be in your mind. You should know that we would separate the whole expression into pieces, in particular 2 here. In algebra, we may actually take out the common factor. In this case, of course, 2. Now, you may carry on with the steps on the terms inside the bracket. You will finally come up with this. Which may be written in terms of f of x. With the given f of x, you may apply the technique from session 5 for sketching. This is the end of the session. Please take some trials with different coefficients. You may use square CO6 to check your answers. Finally, thank you for watching the clips. See you.